6, right? Then 5 and 10, 15. 10 and 10, 20. 15 and 6. And now you should be able to write the next row as well, right? Because you know the pattern that the powers come down on A and the powers come up on H. So this is named after a mathematician, last name Pascal. Pascal, he did not discover this, all right? The Chinese discovered this way before Pascal discovered it. But like a lot of things in history, people get credit for things that aren't theirs, right? So this has been known for a long time. There's pros and cons to this idea, right? The pro is that it gives us a way of getting expansions, right? These are called binomial expansions. These are binomials, two terms. Expanding means multiplying them repeatedly, right? So these are called binomial expansions. This is nice because it gives us a way to calculate them. The drawback to this is that if I wanted to know what a plus h, let's say to the 13th power is, what would I have to do? I'd have to go down the triangle, wouldn't I? I'd have to go all the way down until I get to 13, which is a lot of things to draw, right? Or if I change that to the 30th power, imagine how big the triangle would have to get before you could get that to me, right? So the question is there a better formula that you can go directly from this to its expansion without having to draw Pascal's triangle, right? And the answer is yes, okay? It requires what's called a Maclaurin series, and it is something that you do in Cal 2, right? So in Cal 2, if any of y'all take me, guaranteed, for sure, we will do the binomial expansion using what's called a Maclaurin series, and we will have a formula for doing this expansion without having to draw the whole triangle out, all right? But for here, for now, is where we are. So I want to do one more line before we wrap this idea up. I would like to know what would happen if I did a plus h to the nth power. Now, I'm not going to be able to fill this out completely, but at least we can get some idea of what's happening. What would be my very first term? What would be the number? 1, right? So I'm just going to, 1, and then a to the n power, right? A to the n, right? That would be my very first piece. All of these match, right? 6th power, a to the 6th. 5th power, a to the 5th. 4th power, a to the 4th, right? So a plus h to the n, the first one should be a to the n. Plus. Now, some number, right? Do you know this number? No, but maybe you do. Look at the table. What's that? I'm talking about the number that's in front. So like this 6 and that 5 and that 4 and that 3 and that 2, right? Isn't this number that number? Isn't this power that second number? Isn't this power that second number? Y'all see that? The number in front of the second term is always the power of what you started with. So what should be out here? N, okay? Now, what happens next? We should have a, what should the power on that be? 1 less than that, right? So if it was 6, it's 5. If it was n, it's n minus 1. What should the power on h be? H, right? Just h to the first power. Do y'all agree we know that much? I know the first term is a to the n. I know the second term is whatever power was here times a to the 1 less than the power, and then the h appears, like starts to show up, right? Now the rest of it, I don't know, except for the very last one, all right? So let me put this, plus, do y'all agree the next one, I don't know what the number is in front, don't know. But I'd have a to what power this time? It comes down again, right? So what happens if you take 1 away from this power again? You get n minus 2 and minus 2. And now what's the power on h? H to the second, right? So the powers on n are coming down, the powers on h's are coming up. And I'm just waving my hands, I don't know the numbers, all right? I know the first number is 1, I know the second number is n. Next one is going to be some number, I don't know what it is. A to what power? n minus 3, and what's the power on h? H to the third. You with me? Plus dot, 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 meaning there's a bunch of crap in here, right? That keeps this pattern. A's are coming down, H's are coming up. Until I get to the very, very last one. So what's the number in front of the last one? 1, right? 1, and then h to what power? The nth power, right? The last one is always going to be that variable h, but then to the nth. You all right with that? Yeah, n is just some, well, it's going to be a positive integer, so it's, you know, or non-negative integer. So it's either 0, 1, 2, 3, 4, 5. So I'm coming up with a generic formula that if I ever see a plus h to the nth power, I can actually write it like that. Now, do y'all see that there's a bunch of dot dot in here that I don't know? And that seems like, okay, that's a problem, right? We don't know what that is. But while this is fresh in your head, I think I'm going to show you why I gave you all of that, all right? I'm jumping a little bit ahead, but I'm going to show you, all right? Today has been about me giving you a function and me asking you to find the slope of the tangent line, right, at a number or at a, right? That's what today has been about. And there's two definitions you can use, yes? Two different definitions. So here's the new problem. I'm going to leave that on the very bottom. I'm going to leave it there because I need it. This will be a nice wrap-up of what we've talked about today. Man, what is going on? Here's your function. Let f of x be x to the, I don't know, what do we want to do? We've already done squared, right? We've already done fourth power. We can do fifth power, right? Sixth power. Why don't we do the nth power? How about I just like leave it as a variable? Just x to some power, right? And I want to know the slope of the tangent line. Find the slope of the tangent line at x equals, and I'm not going to give you a number, I'm going to give you a generic point, so at a. See, what I'm trying to do is generalize. I'm trying to find a way to find the slope of the tangent line at some arbitrary point of x raised to some arbitrary number. And if I can find this, then I will have a nice formula, won't I? All right, we get two different options in terms of the definition, right? There were two different ones I can use. So let's take a look at those side by side. The first definition and the second definition. The first definition is the limit as x approaches a of f of x minus f of a over x minus a. That's the first definition. The second definition is the limit as h goes to 0 of f of a plus h minus f of a all over h. I realize it's almost 4, you're tired, I'm tired, I'm losing my voice. We're going to grind this out. We're going to have a very nice result at the end of this. I think the only person I haven't called is Jennifer. No, and Nicholas has already provided us an expansion of something, so Nicholas, you're good. Jenny. Apologize. Yes? Okay. Help me fill this out. What's this? Okay, so no, think, what is the original function that I gave you? X to the n, right? You don't know what n is, right? It's just x to the n, right? So this is limit x approaches a of x to the n. Now, Jenny, minus a to the n. Good, minus a to the n. That's plugging a into this function over x minus a. Do y'all understand where all that came from? Let's continue with this before I do the second definition. What algebra can you do? You can't do like any of this, right? Cancel. You can't do that, right? Because there's subtraction between these. You can't. That's not the way reduction works. You have to have multiplication, right? So is there any algebra that you know that you can do here? I'll tell you, you can't, okay? There's no algebra you know. Now, if these are even numbers, if n was even, then yeah, maybe you could do difference of squares, right? But if they're odd, you don't have anything, right? So generally speaking, you do not have a way of doing this. So right here, we are stuck, okay? We are stuck with the first definition. We cannot figure out what that is. However, if we use this definition, we do the limit as h goes to 0. When I plug a plus h into that, a plus h into this, don't I get a plus h to the nth power? Isn't that what I get? Then minus what? A into that? A to the n over h, right? That's the second definition. Now here we were stuck, right? Can't do anything to the top. You're trying to get the x minus a to cancel. Can't do anything. Here, I still can't do anything in terms of like looking at this as like a difference of powers of n, but do we know what a plus h to the n is? Well, kind of. We know some of it, right? This is what it looks like. There was a bunch of dot, dot, dot in there that I didn't know, right? Right? But I can at least say this much, can't I? So I'm going to use this now. Keep in mind, everything I have right here is just the top left corner of this. So let me write it out. I have limit h goes to 0. Okay, a plus h to the nth power. I'm about to write everything down here. So I have a to the n plus n times a to the n minus 1 times h plus some number I don't know, a to the n minus 2 times h squared, plus, I need to erase, some number I don't know, a to the n minus 3 times h cubed. And I keep doing this, right? I keep doing this, plus dot, 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 until I get to my very last term, which is h to the nth power. That's just this, isn't it? That's just that. What do I still have to do? Subtract a to the n, right? I still have to subtract a to the n. So I have to erase this because I'm running out of room. If I subtract a to the n, and then put all of this over what? H, this very nice thing happens. I heard y'all say it. The a to the n's go away, right? Yes? You see it? Every single one of these terms that's left has an h, right? That has an h, right? That has 2 factors of h. This has 3 factors of h. All the way down to the very last one has n factors of h. So do you all agree I can pull a GCF out? Yes. I can pull a single h. Let's pull that single h. If I pull the h out, let's see what happens. If I pull h from here, what am I left with? N times a to the n minus 1 plus some number I don't know, a to the n minus 2 times h, right? Because I pulled one of those h's. Plus some number I don't know, a to the n minus 3 h squared, because I pulled one h from here, plus dot, 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 dot. My very last h I pull out, I should have n minus 1. Whatever that power was, I now have 1 less than that, don't I? All over h. And the h's go away, right? And now, looking at this, what can you tell me about every single one of these in red, even all the ones that I don't even know? What do they all have in common, Nicholas?
H.
They all have at least one H, right? You all agree? Everything in red has at least one H. And I'm about to let H go to what? 0. So this is going to go away, that's going to go away, that's everything in there, in the dot, 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 it's all going to go away. The very last one goes away. The only thing left is what? N times a to the n minus 1. And I've taken the limit, so no more limit. N times a to the n minus 1. Holy shit. That is super powerful, right? Look what we've done. We have found a formula that will give you the slope of the tangent line at any point for any function that is just a power of, x. So I want you to appreciate how powerful this formula we just got is. What was the first problem today? X squared, right? We started with this problem, f of x was x squared, and I wanted to know the slope of the tangent line where? It was 2, right? Right? Okay, so first things first. This is an x to the n, isn't it? That's an x to the n. What's n for us? 2. So according to this formula, this should be the slope of the tangent line at a. Right? So for us, it should be the slope of the tangent line at x equals a, not at 2, but at x equals a, will be, for us, n was 2, right? N was 2. So it should be 2a to the 2 minus 1, which is just 2a, right? 2a. 2a is the formula that gives me the slope of the tangent line at any point. Now plug in 2. What do you get if you plug in 2? 4, and that's what we got, isn't it? I know I went faster than that, and we're going to definitely revisit this again.
So you basically just use that for anything?
For any x to a power. And later on, this is actually going to be called the power rule, but we're just not ready. I got a little ahead of myself. Okay, so look, as far as concepts, we're done. I just have to wrap one last little thing around this. It's all about notation, okay? So you know how I've been writing on the board, find the slope of the tangent line, find the slope of the tangent line, find the slope of the tangent line, and it's just kind of got repetitive and kind of a pain in the ass. So mathematicians, we don't like to write words. We like symbols and notation. So we have another way of asking you to find the slope of the tangent line. It's just a notation, right? So let's do that. Let's talk about the notation. We're going to have some language that goes with this notation, and then we're going to wrap it up. Still in 2.1. Yeah, we're not there yet. Yeah, it's okay that we're still here. We spent a good amount of time. All right, so here it is. All right, the two formulas that we have from today that give us the slope of the tangent line at some value a are these two, right? I think I beat this in enough, yes? These are so widely used that we have a special name and notation for those two limits. It is called the derivative of the function f at the number a, right? So the derivative of the function f at a is simply the slope of the tangent line at a. Those mean the same thing. The slope of the tangent line at a is the same as the derivative of the function at a. And the notation we use for this is f, which is the function, and we put this little prime, it's called the prime mark. It's like an apostrophe, but it's this, we call it prime. We write f prime a, and what that is, okay, this notation means that limit, or if you want, you can use the other limit depending on, your choice. They give you the same answer, so both of those are identical. So the way you say that, right, you can say it two different ways. That's the derivative of f at a, or you can say f prime of a, f prime. This little mark is called the prime mark. So you can say f prime of a, or you can say the derivative of f at a. But all it means is the slope of the tangent line there, right? All right, I think I've done enough examples for now. All right. Now, this is just a little bit more about the geometry of this. The derivative, right, this f prime of a, not only does it represent the slope of the tangent line, right, that slope of that tangent line can actually have some meaning to it. It can also represent what we call the instantaneous rate of change of the function at the number a. So I want to take you back to like our first class where I was talking about, I think I was talking about driving to Austin. Do you remember me saying that? If you have here time and you have here, let's say, distance, right? Then if it takes you 2 hours to go, I think I said 70 miles. Let's say 2 hours. Your average speed would be what? 35. And the way I said you do that is you connect these two together, right, with a straight line, and you find rise over run. Rise is 70, run is 2, 70 divided by 2 is 35. So the slope of that, what kind of line is this that connects 2 points like this? Secant line. The slope of the secant line is your average speed, right? The slope of a tangent line is what we call the instantaneous speed. So now if I say, all right, go to some point in your trip, let's say right here, okay, call that A, go up to this, then whatever the slope of that tangent line is actually the speed you were going at that instant in time. So if you look down at your speedometer right then, your speed on your speedometer is your instantaneous rate of change. It's your instantaneous speed. Which was, one of the fundamental problems, I guess, with the calculus was, is it possible to talk about the speed of something at an instant? Right? Because we said in an instant you don't move, there's no time, so you shouldn't be able to define it. We have actually found a way now to define the rate of change of something at an instant, which is, that's the big takeaway of Cal 1. Now, any questions? Average rate of change. Yep. Secant line is average rate of change. The derivative of the function at a is the instantaneous rate of change. This does not have to be, you do not have to be looking at time and distance. This can be any two quantities that you can think of. And then it still represents instantaneous rate of change. So let's say we're doing a chemistry experiment and we're measuring, let's stick with time, okay? Let's say we're measuring things in seconds, right? And let's say here we're measuring the temperature of something, right? In Fahrenheit or whatever you want, right? Then when you run the experiment, maybe your temperature, maybe it drops and then increases and then drops and you wind up here. So you could ask the question, what's your average rate of change of temperature? Which would mean, what's the slope of that secant line? But with calculus, we can actually go to any point in the experiment, any point in time, go to the function, and find the slope of that tangent line, and that would be your instantaneous rate of change at that moment. Here it would not be miles per hour. What would it be? Like in this, the slope of this line, I really want to make sure I connect this, and I should have said this before. The slope of this line right here in this picture is rise over run, right? Slope is rise over run. What's rise? Miles. What's run? Time. Miles over time. Miles over hours. Miles per hour, right? So this slope is your miles per hour. It's your speed. Here, what's the slope of this tangent line? It would be temperature over seconds. So it would be your instantaneous rate of change in degrees per second. Miles per hour, degrees per second. Okay? But this extends to anything, right? Any physics, chemistry, biology. Our ability to find the instantaneous rate of change of something is profound in terms of human existence. Our ability to do this is big because we don't have to look at averages anymore. We can talk about things at that exact moment. So calculus really opens that up for us. All right. So I think that last definition there, I'm almost done. Promise. We're going to end early today because my voice is about to go. Was that a sigh of worry? Are you worried? Okay. Oh, you're ready to go. All right, so the derivative, f prime of a, not only represents slope, but it's instantaneous rate of change. All right, instantaneous velocity. So this is the one particular case that I've already drawn on the board several times. If this is distance and this is time, then we're talking about velocity. Distance over time is speed, speed and velocity. Are speed and velocity the same thing? No, yes and no. Velocity needs a direction. So this depends on how much physics you've taken. If you have an object moving in a straight line, then velocity and speed are the same thing. Now, if you're moving in like, not a straight line, then velocity and speed are not the same thing. So when we're talking about velocity here, it's for straight line motion, all right? So that way we don't have to worry about vectors and all that. So if we're talking about an object moving in a straight line and you have time here and distance here, then the instantaneous rate of change or the instantaneous velocity will be the tangent line, right? The slope of the tangent line. I've drawn this too many times. I don't think I need to draw it again. So I don't remember what this does. So let me move it here. Yeah, there we go. So that would give us the slope of the tangent line right there would give us the instantaneous velocity. All right, this is a very natural place to stop because like I said, when we transition to 2.2, you're like, wait a minute, now we're switching over and it's confusing. So I think if we stop here, send you home to do your homework, it should be a natural transition when we come back. For homework, I already gave you everything. 21, 23. Oh, sorry, I forgot. Let me write it on the board. There's more. I forgot these here. Okay. You shouldn't have asked. 1 through 6. Seventeen, 21, 23, 25 through 30. Now, on problems 1 and 2, only do parts A and B. There's parts A, B, and C. For part C, don't do part C because they're asking you to use a graphing calculator to graph. You don't need to do that. If you'd like to, go ahead. Go to Desmos, graph something. But for 1 and 2, only do parts A and B, and then this is the complete assignment. All right, I do plan on having a quiz. All right, I'm trying to give you one every week, so I think a quiz next class. All right. Make sure that when you come to class, bring your notes, bring your homework, because I told you on the first day that it is possible that I give you a quiz where you're allowed to use your notes, right? I did say that that's possible. So I would hate for you to show up and be like, man, he let us use our notes or homework, but I didn't bring my homework. So you've been warned, right? Yes, bring it. Have a great day, everyone. Let me turn the camera off. Is that all right?
That's 2.1, right?
That's 2.1. Yes, I'm sorry, I wasn't clear on that. That is 2.1.